Are you guys there?
Yes, doctor.
Yes.
Okay, what did we learn about the energy equation? Okay, so I think before we start, we begin with Ulmu Kita Al-Fatihah for Muslim. Okay, so the last class, we learned about the energy equation. How to derive the energy equation from the system to the control volume by using the Reynolds transport theorem. Inside the Reynolds transport theorem, we have two categories, which is control volume and control system. Okay, do you still remember the final version of energy equation? This is very important part. The final version of energy equation. Okay, the final version of energy equation, which is include the Bernoulli equation, which is V1 squared over 2G. This is for uniform flow, yeah. Plus pressure 1 over gamma, which is rho and G, plus Z1, plus we have the work shaft, alright, the work from the pump or from the turbine. Okay, this is at the inlet one. Turbine or pump? Pump or turbine? Anyone? This is work from the pump, because pump should be at the inlet. Okay, over mg dot. This is the final version. Okay, the same thing. V2 squared over 2g plus P2 over gamma plus Z2 plus this is work shaft from the turbine over mg and plus 1. Do you still remember another one, which is loss? Okay, heat loss. Okay, this is Bernoulli. This is work of pump. Okay, this is losses. That's it. Okay, so let's try to work out on this example. Okay, the venturi shown reduce the pipe diameter. Okay, guys, the venturi meter here reduce the pipe diameter. You can see from 1 into 2 to a minimum 50 millimeter. Calculate the flow rate and the mass flux assuming ideal condition. That means ideal condition it is assuming it is uniform flow. What the uniform flow? This is pipe. The velocity is uniform across the section. This is velocity. And then it is incompressible. Okay, the change of the density is less than 3%. And finally, it is steady flow. There is no change of property over time. Okay, this is the assumption, 3 assumption. Okay, the question asks find the flow rate. Okay, you look at here. Okay, we have the flow. Alright, from point 1 to point 2. So first, what we need to do? okay, we can apply the energy equation because this is moving. Definitely, we have the kinetic energy, we have the potential energy, we have the loss. So we have to consider using the energy equation because it is moving. Alright. So based on energy equation, which is P1 over gamma plus V1 squared over 2G, because we have one inlet and one outlet. Inlet is 1 and outlet is 2. Plus Z1 plus work from the pump mg equal to, when you deal with this energy equation, write all the term, remember, and then you can cancel out. And then this is work from the turbine. This is power, power from the turbine, mg plus heat loss. Okay, once we consider it is ideal and it is very short, we can assume the loss is equal to 0. And do you see we have the machine, turbine or pump? No, right? We don't have any turbine, cancel. We don't have any pump, cancel. Do you think the height, the elevation at point 1 to 2 the same? Yes, Z1 and Z2 the same. Okay, the same level. Okay, you can see V2 and V1 the same level. We can cancel out. Okay, what do we have now? We have pressure 1, pressure 2. Let's rearrange pressure. Okay, rearrange pressure. I want to transfer the left side to the right side. So P2 minus P1 over gamma. Okay. And then V plus V2 squared minus V1 squared over 2G equal to 0. This as equation number 1. So far you guys understand until this part? Everybody? All of you understand until this section?
Yes, doctor.
Okay. So thank you for respond. All right, next. We have 1, 2, 3 unknowns. All right, 4 unknowns. So how to get another equation? Okay, it is coming from where? Anyone know? First, we have energy equation, the horizontal section. Can you see the bottom part? We have
manometer reading.
Manometer. This is manometer reading. So we should have another equation from manometer. Okay, good. Manometer. Okay, this is interesting. When we deal with manometer, we should put the line and the reference line. Okay, deal with manometer. Okay, you can see here. This is A, and cross section here. This is B, and this is C. Okay. All right. So what should we start here? We can start from anyone? Okay, we can start from here. All right. From point number 1 to point A, and then A to B, B to C, C to point number 2. You guys, okay? This is point number 1. And this is point number 2. Let's say this is the point. And this is the point. Okay, we start from here. Alright. So, P1 minus PA or PA minus P1. Everyone?
PA minus P1.
P?
A.
PA minus P?
A1.
Okay, perfect. Negative gamma. Gamma of what? Anyone? Gamma of what?
What? Water.
Yes, gamma of water. ZA minus Z1. Okay, gamma of water. What's the gamma of water? Okay, it's okay. Negative gamma. Okay, Z. Okay, ZA. First, we should set up the reference line. This is very important. Okay, let's say this is our reference line, yeah? From A to 1, okay, what's the value? From A to 1, what's the height? What is the Z? What is the Z1?
1.2 plus 6.
Yes, perfect. 1.2 plus Z, we will have Z1. So, okay.
فهمت أنا بدل مانومتر فهمت.
Okay, you can see ZA. ZA is at the reference line. It is 0. Minus Z1, which is Z plus 1.2, which is here. Okay, negative Z, negative 1.2, because it is plus. When you deal with negative, negative always win. Okay, so after PA, after 1 go to A go to B. Do you think necessary to put A to B?
No.
No, because it is the same pressure line. So B to C. So P, PC minus P, PB. Negative gamma of mercury, ZC minus ZB. Equal to negative, this is water, yeah? Sorry. This is water. This is gamma of mercury. Alright. ZC, what is the value of ZC? Which is 1.2 minus 0. Okay. And then, the last, the final. From C to 2. Okay, this line. From C to 2. So P2 minus PC. Okay, P2 minus PC.
PC.
Negative gamma of water. Z2 minus ZC. Negative gamma of water. Alright, Z2. What's the value of Z2?
Z.
Z. Where's your reference line? What is the value of Z2?
Z plus 1.2.
Yes, Z2 is Z plus 1.2. Okay, minus ZC. What is the value of ZC? 1.2. Okay. So from here you can cancel out. So what you need to do? Plus everything here. PA equal to PB. PC cancel with PC. So we have P2 minus P1. Okay, you solve this one. Okay, you will have. Okay, I solve it for you. Okay. Okay, this one, yeah, the bottom, the middle part. And then this is cancel. Cancel. We have negative Z gamma of water. So can you see we can cancel out this one? This one, the same with this one. So what we only have now, we have P2 minus P1 equal to factorize 1.2 gamma of water minus gamma of mercury. Okay, up until now, up until here, do you guys understand for this part?
Yes.
Okay, understand, yeah? Okay, so this is equation 1. You can see equation 1 and equation 2. Okay, so you can see from equation 1, this is P1 minus P2. This is P2. This is P2 minus P1. This is also P2 minus P1. So how to form this section? The first part, we can divide all this with gamma. Okay, in order to substitute. So this is gamma of water, yeah. See, so we will only have 1.2. This is gamma of water 1 minus gamma of mercury over gamma of water. So let's say this is equation 2. Can you substitute equation 2 into equation 1? Yes, right. We can substitute equation 2. Okay, substitute equation 2 to equation 1. Alright, so I try to substitute. Okay, so 1.2, 1 minus gamma of mercury over gamma of water plus V2 minus V1 squared over 2G equal to 0.
0.
Okay, so we have gamma, definitely we have gamma of water, gamma of mercury we have. So how about velocity? Do we have the velocity too given? The velocity is not given, but it is given the cross-sectional area. Remember we learned the continuity equation. Okay, our continuity equation said that Q1 equal to Q2, which is volume flow rate at point number 1, the same with volume flow rate at point number 2. So Q we expand into A multiplied with velocity. Okay, A multiplied with velocity. Okay, now I want to make the V2 as the subject. So V2 equal to A1 over A2 multiplied with V1. So what is the area shape here when you look at here? What is the area shape? Is it rectangular or circle?
Circle.
Circle. Area is circle. Okay, what is the area of circle? Pi. Okay, pi diameter squared over 4. Alright, so substitute area 1, which is pi d1 squared over 4 over pi d2 squared over 4 multiply with v1. So from here we can cancel out pi, 4 and 4. And finally we'll have d1 over d2 squared and squared v1. Okay, so this is actually v2. So v2 is equal to d1. Okay. Okay, d1 over d2 squared. So what is the d1? The diameter of, it is given that the diameter of d1 is 100.
100.
100. So in millimeter, which is in meter, which is 0.1 meter. And this one is 0.05 meter. This is diameter 2. And this is diameter 1. Okay, try to substitute. Here, d1 is equal to 0.1 squared over 0.05 squared v1. So what's the answer? Okay.
4v1.
Perfect. Laju je. 4v1. V1. So we can say V2 relationship with 4V1. Okay. So can we substitute here this value into this? Yes, definitely we can substitute. Okay, so try to substitute. Okay. So 1.2 1 minus, okay, specific weight gamma of mercury. How to get the gamma of mercury? You know that gamma of mercury is equal to specific gravity multiplied with gamma of water. So this is specific gravity of mercury. So what's the value of specific gravity of mercury? Okay, the specific gravity of mercury is here 13.6. Okay, this one is actually you can look at from the table Sg of mercury, and the question normally will give you, don't worry. Alright, so for this case the question, I believe it is not given. Okay, so the Sg of mercury I give for you 13.6. Okay, normally it will give, don't worry, yeah. So replace the specific weight. Okay, so specific weight of mercury, which is 13.6 gamma of water over gamma of water. Okay, I think you can cancel out this part and this part. Okay, V2, which is 4 V1.
V1.
Put the bracket, alright? Square. The 4 also inside the bracket. Over 2G equal to 0. Alright, solve for, you try to solve, you will get negative. You solve this one and then multiply 1.2, you will get negative 15.12. You solve this one, you will get 15V1 squared over 2G. Then I believe you can solve for V1. Okay, so V1 answer is equal to 4.45 meter per second. Okay, so far until here, you guys understand how to get the V1 velocity at point 1? If you have any question, feel free to raise your hand or ask me any question, okay? Okay, so the question asks, calculate the flow rate. The flow rate, what is the flow rate? Which is a volume flow rate. Q, whatever Q1 or Q2 the same. So since we have the V1, should we get Q1 or Q2, everyone?
Q1.
Q1, because we have area 1 and velocity 1. So area 1 pi diameter 0.1 squared over 4. This is pi d squared, yeah? Multiply with velocity 4.45. The final answer is 0.035. What's the unit? The volume flow rate? The unit. When you answer the question in the exam, please put the unit correctly. Meter cube per second. The unit of gamma is Newton, yeah? Newton per meter cube. You need to remember this. Alright. So next the question asks the S, I think. The mass flux. Alright, mass flux. That means mass flow rate. Mass flow rate is the symbol m dot. What's the value of m dot? What's the formula? Which is rho multiplied with Q. We have Q. We don't have any rho. Do you have the rho of water? Yes, the rho of water is 1000. This is standard, yeah? Multiply with Q. This is the Q. 0.035. You will have 1, 2, 3. So 35 kilogram per second. Okay, guys, do you guys understand until this section?
Yes.
Okay. Okay, that is the example that you must understand. Okay, when you look at the venturimeter, it is different. Okay, what happened when the venturimeter? Okay, I think this one. Okay, when you deal with the venturimeter, you should look. This is the pitot tube, pitot tube meter or just a manometer. Okay. Okay, the one that you learn, this equation, energy equation, is for the assuming ideal condition, which is uniform flow, incompressible, and steady flow. So what happens when you deal with the non-steady, non-uniform flow? If the uniform velocity profile cannot be used, the velocity distribution could be corrected. Okay, this is what I mean. Previously, we learned about uniform flow. This is uniform. And this is non-uniform. Okay, this is flow, yeah. So let's say this is the part. Okay, and then we have the water section. So the water for the uniform from here to here the same. We ignore the friction. The pipe friction, it is the same. Uniform, you can see, uniform, the standard, the same length. However, for non-uniform, it is like this. Why? Because we consider the friction along the pipe. That is why it is holding this velocity back. Okay, so when we deal with this case, you can see non-uniform flow. We must use the corrected, okay, corrected kinetic energy. So basically, this is the, I don't want to show you the derivation, it's quite long, but this is the kinetic energy correction factor, alpha. Alpha equal to integrations of velocity cubic dA cross-sectional area over average velocity. This is average velocity cube dA. Okay, can you see it is dA, V cube cancel each other. That is why we call as a factor. No unit. Alright. So later on, I'm going to explain to you where the alpha located. So the term that account the flux in kinetic energy basically is this one. This is the flux in terms of flux. 1 over 2 rho integral of area V cube dA equal to 1 over 2 alpha rho V cube. Okay. V cube. Okay, sorry. This is not have a D or dA. Okay, you look at here, from here, we convert into here. You can see when you try to multiply alpha with V cube A, you will have this term. Okay, and then the numerator part will have this term. Alright, and then this term only plus the density. Density and density is constant. That is why we call it as a flux. Okay, and 1 over 2 constant. This is in terms of flux, yeah. With V being the average velocity, you can see the V here, the V cross line. Therefore, the final equation that account for this non-uniform velocity is, remember that previously, this is the previous equation, which is V1 squared over 2g plus P1 over gamma plus Z1 plus work of the pump mg equal to V2 squared over 2G. This is final version for the energy equations. This is work of the turbine and plus heat loss. Okay, when we deal with the final energy equation for this non-uniform velocity, we should alter this part because the velocity is not uniform. It is non-uniform. Okay, like this, the velocity moving profile. Alright, so here, the velocity here will be like alpha 1, okay, velocity 1 squared average over 2G. Okay, and the rest is the same. Okay, this is the difference. Alright, this is the final version for energy equation when dealing with the non-uniform flow. Okay. Alright, in order to strengthen your understanding for this case, let's try for this equation. Can you see what the velocity looks like? Everyone, this is uniform or non-uniform flow? You can see this is, the velocity is not uniform, right? It is non-uniform flow because we have the curved line here. So example 4, the velocity distribution for a certain flow in the pipe is given that, okay, this is the equation. Okay, this equation. VR, so that means velocity with the function of R. Changing the R will change the velocity magnitude. So this is V max bracket 1 minus R squared over R naught squared. So when you look at from this section, you will have this view. So from here, okay, you can see the R. R is changing. R naught is the constant. Okay, R naught from the center to the outside of this, the outer of the pipe. And this is the small change we call as the dr. And this is R. This is the analysis. Okay, so to find the kinetic energy, this is the question asked. Determine the kinetic energy correction factor, which is alpha. So to find the alpha, we must know the average velocity. Okay, because why? You look at here, you see we have the average velocity cube multiplied with the area. Okay. So based on the equation, basically this is the previous equation, yeah. Okay, based on the equations of okay, to get the alpha, we must find V average first. Okay, how to get the V average? It is combination from equation in the textbook Porter, which is equation 4 and 10, and equation 4, 4 and 11. This is the final equation. Okay, you can look at from the textbook, yeah, this equation combined, you will have the V average equal to integrations of V dA over A. Okay. It's okay. Let me show to you the Porter equation. Okay, equation for 10. Control 4 and 10. Okay, equation 4 and 10 and 4 and 11. You look at here. This is the volume flow rate, all right, across the pipe. Okay, so Q equal to integrations of V and dA. This is the continuity equation, and this is the average one. You can see basically the same, Q and Q. So we can equate this equation with this equation. That is why equation 10 and equation 11, we can equate them together. And finally, we'll have this equation. All right, so from here, okay, the area. What is the area of this circular? What is the formula? Anyone? 1 over pi r. This is the area. The area is constant. We should use the r. R naught or r? Everyone. R naught or r? The whole area.
R naught.
Yes, we should use r naught. Pi r squared. Okay. So just put this equation. This is, we move outside. Integrations of 0. This is with respect to area, yeah. From 0 to r naught. Okay, you look at here. From 0 to r naught. We need to integrate from the center to the outer of the pipe. So that's why from 0 to r naught. Okay, so this is V. V is this function, which is V max. Okay, V max. This is the equation given, yeah. Bracket y minus r squared over r naught squared. Okay, and dA. dA is given by 2 pi r dr. 2 pi r dr. Okay, so from here you can see V max is constant. We can move outside. Okay, what we have, 2 pi is 2 pi. Okay, 2 pi is constant. The r is not constant. Okay, 2 pi we can move outside. Okay. So simplify this equation. Okay. We will have this one. Okay. Pi cancel with pi. Alright. We will have 2. This is 2 V max. Alright. Over this one R naught. Okay. So this one integrate from 0 to R naught. 1 minus R squared over R naught squared dr. Okay, now you can do the integration. So after you do the integration, you will have this final. Okay, 2V max over R naught squared. You integrate this one. Okay, this is R. Integrate with this with respect to this. Okay. So yeah. Okay, you look at here, we have the r here. Okay, we can multiply this one and this one. So we will have r here, and then this is r. Okay, this is r cube. Alright, so r, integrate with r, which is r, okay, 2 over 2 minus r4 over 4r naught squared. This is r naught squared is the constant, yeah? Okay, this is r naught, this is 0. Okay, substitute, you will get the value of 2. Okay, you will have all the value here. I try to simplify. Okay. Okay, 2 Vmax over r naught squared. Try to substitute this one. R naught squared over 2 minus r naught 4 over 4r naught squared. This is 0 and this is 0. Okay. Okay, so from here you can solve. I think you can solve. Okay, you can get the final answer is 1 over 2 Vmax only. Alright. So next is this is the velocity average, which is half Vmax. When you try to solve this one, okay, I believe you know already. Okay, when I hope you know how to solve this one, yeah. Okay, so you will get this final value. Okay, so using the equation here, you can see here alpha, which is okay, using the alpha, which is equal to integration of v cube dA over integration, v average cube dA. Okay, so integrate from 0 to r naught. So v is here. Okay, this one v, which is Vmax minus 1, Vmax bracket 1 minus r. So bracket Vmax, okay, this is bracket, yeah, 1 minus r squared over r naught squared. Okay, this is bracket, this is cube, multiply with area dA. dA is given by 2 pi r dr. Just substitute here, 2 pi r dr, and then over with v cube. Okay, v average. V average is the one that we found here, half Vmax cube and dA. Okay, sorry, this is not the dA, this is area only. Okay, because you look at here, v cube area. Okay, no differentiation here. So how to get the area? The area is fixed by r squared. So r is r naught. Use this area by r naught squared. Okay, so pi can cancel with pi. Okay, when you do this integration, finally you will have this value. Okay, you try to solve this, integrate. Basically, this is quite take a long calculation, because this is the power of 3. You have to multiply 3 times. Okay, this is the final one I give to you. 16 over r naught squared bracket r naught squared over 2 minus 3r naught squared over 4 plus 3r naught squared over 6 minus R0 squared over 8. Okay, and the final answer is 2. It is very difficult only to get 2. Okay, so now our alpha here, the correction, kinetic energy correction factor is equal to 2. Okay, do you have any questions so far? You guys have any question?
Oh, thank you, Doctor.
Okay. I think that's all for today. Okay, if you have any question, feel free to let me know. Please be ready with your test 1. Okay. It is more on apply. Okay. Please revise for what I have taught you before. Okay, and then please put initiative to get revision from other textbook, because you are not here to spot the question out. You are here to learn what the question going to be solved. All right. So you are here to solve the question. You need to understand the fundamental. Okay. For those who haven't scanned, please do scan your attendance section. Okay. So tomorrow at 8:40 p.m. Okay, please be on your screen. The link for the Google, we're going to use the Google Meet. All right, I will be the host. I will conduct the briefing about the section, about the set. We have set 1 and set 2. I'm going to explain to you how we're going to differentiate set 1 and set 2. Please be ready, Okay. I think that's all for today. I hope you learn something from today's lecture and improve your fundamental skill. Okay, I end my session with Assalamualaikum warahmatullahi wabarakatuh and selamat berpuasa.
Thank you, Doctor.
Okay, welcome.
Waalaikumsalam, Doctor.
Okay, waalaikumsalam.
Excuse me, Doctor.